Okay,
Yeah.
good. So our first speaker today is Moshe HAIUT. Moshe is a principal senior engineer in the CTO team at DSP Group in Herzliya in Israel. His main areas of expertise are communication, video and audio, digital signal processing, digital hardware architecture, and neural networks. He holds an MSc with honors and a BSc with honors in electrical engineering from Tel Aviv University and from the Technion in Israel. And he's the architect of NNet Lite, which is an ultra-low power hardware engine for neural network inference. And today, Moshe will talk to us about innovative and convolutional-friendly tinyML architectures for small silicon low-power devices. And Moshe, the floor is yours.
Okay, thank you, Ofer, for an excellent introduction, and welcome everybody. I will talk about the NNet Lite, which is an engine that was especially designed for running inference of neural network models in an always-on mode, and it will be integrated in our future chips, in our future multimedia chips. So let's begin with the requirements for this NNet Lite engine. The first requirement was that it should run small to medium neural network inference models. And there are some examples for this. Wake word detection, sound event detection, and voice activity detection. And also from the video domain, face detection in QQ VGA size of frames. It should be low power, ultra low power. So it goes from 1 milliwatt down to tens of microwatts for the smallest target neural network model. Limited silicon area and programmable, it should be programmable so that it is not dedicated to a specific model that we design. Let's go over the block diagram of this engine. So there is an embedded controller unit, which is based on the RISC-V CPU. And this runs some software, so it consumes too much power for such an ultra low power design. So most of the time it goes to sleep, actually. And between the layers themselves, it wakes up, and then it configures the setup for the next layer, and then go to sleep again. And finally, at the end of the inference, it communicates with the host controller. There is a bunch of configuration registers that actually contain the descriptor of a full layer, as I said before, and this run without independently of any other external assistance for a whole layer. And this is the input, the data buffer of 8 kilobyte SRAM. And there is the interlayer memory, which is actually the activation memory. It contains the activation data for the input and output of a single layer. And it is a 128 kilobyte SRAM. The mark unit is a single mark unit in this design, and we'll talk about this. And there is a pooling logic unit that can make pooling on the fly. We'll also talk about this. We compress our weights after they are being quantized. And this weight extraction unit has to extract them and arrange them in a 16 kilobyte SRAM as a cache memory for the current computation only. So the memory is very small, even though the weights can occupy about 1 megabyte of memory. There is an address generation unit. The role of this unit is to produce the addresses for these two memories, as you can see, and in order to provide the MAC with its operands in real time. And there is an activation function unit that is liable of making an activation function within 2 clock cycles. All these units are actually pure hardware. Else we are talking about the ECU, which is sleeping most of the time. Okay, so let's go now to see the Mach unit. As I said before, it's a single unit. And why single unit? Because all our target neural network models require no more than 125 million Mach operations per second. And the clock itself is also limited by 125 megahertz. So if we require that there will not be any wait states, any wait cycles, then we are all set. We don't need more than a single Mach, and this reduces the leakage current to minimum. In the very beginning, by the way, we were thinking about an array of 16 Mach units, but this would consume about 100 microwatt, and this is too much for the smallest target neural network model that we were considering. So you can see here in the block diagram, the AGU, the 2 memories, and the X and W operands that enter the multiple and accumulate unit. This actually moves the challenge into the address generation unit, because the 2 memories, as well as the Mach unit, can do their jobs in a single clock cycle. So let's see why it is challenging for the address generation unit. This is because it has to run not only fully connected layers, which can be implemented in 2 counters, because all the addresses are subsequent addresses, but it has to also support convolutional layers, depth separable convolutional and transpose convolutional layers, and actually all kind of very complicated layers rather than a fully connected layer. If we implemented this in software, then it would require about 5 times the number of clock cycles, and it would consume about 10 times the energy in order to emulate this AGU job. And we implemented it in pure logic. It only has some 8 counters, 12 adders, 16 stage registers, and it is fed by 9 configuration registers as a setup to run a full layer. So it contains some state machines, very complicated state machines to generate these addresses. In this slide, you can see the difference between our approach in the NFLight. The AGU is dedicated for a single Mach unit. That is why its power consumption is very important. It should be reduced to minimum because it is fully added to the energy of the Mach operation, a single Mach operation. And this is in opposed to a typical high-performance neural network architecture, where there are multiple Mach units, in this example, 256 units. So the energy of the AGU, which can run on a CPU and software and consume more than 1 cycle per an address, is divided by 256 when coming to calculate the energy per a single Mach operation. That's the difference. So the AGU is designed for 2-dimensional convolutional layers with sometimes 4-dimensional weight kernels. And we will see some examples of this in the next slides. So the first example is a convolutional layer, a complicated one with pulling on the fly. So why we do pulling on the fly? Sometimes some of the layers produce a huge amount of output data, and it cannot fit on the memory that is on a tiny chip. So we want to reduce the amount of output data by making pooling on the fly. So as you know, pooling reduces the amount of data. For example, 2 by 2 max pooling
Timer. No.
reduces it 4 times in a factor of 4. So as you can see here in this slide, the pooling logic unit, the PLU, only accommodates some register, and it doesn't require memory. It just makes all the job by just updating this register when there is an input that is greater than the value in this register. And also the AGU has to make some different strides over the input map in order to provide all the map series, all the max pooling series into this unit, so that it can decide which is the maximum value. So we can see that in this example, the two-dimensional convolutional layer is it contains maps of 20 by 81 pixels, and there are 16 channels in the input. So there are 16 maps, and it should produce 64 output channels with the 2 by 2 max pooling on the fly. So you can see here the setup for the AGU. It contains 15 different parameters for the descriptor of this layer. And here is the pseudocode that a CPU would run in order to execute this layer. But we do it, as we said, in a single cycle. So you can see here the mock operation in a single cycle, and you can see how long is the calculation of the index, which is actually the address of X and the address of W. Both of these should be implemented in a single clock cycle. So this would require 9 multipliers, 12 adders, and 8 counters. And our AGU does not contain even multipliers, but it does it in a single cycle. So here you can see how we stride over the input map. So the input map is, as we said, 20 by 81, and there are 16 channels here. And here you can see the convolution that is made over 3 by 3 by 16 by this kernel. And the first output of the pooling series is done. And then we go one stride to the right and produce the second one. And then we go down and all the way to the left to produce the third one. And then the fourth one produces the output at the pooling logic unit. So the pooling logic unit does not use memory and only produces the output data, which is only 10 by 40 rather than 20 by 81, which would be if there was no pooling on the fly. So this is one example. The other example that I want to show is a transposed convolutional layer. In this type of layer, the kernel is supposed to stride over the output map rather than over the input map. So everything is upside down, and the output pixels are calculated step by step, not in a single stride. They are updated per every stride. So, and also the padding results in smaller output map in opposed to a regular convolution. And the stride, if bigger than 1, results in a bigger output map, and also the dilation. All of these in opposed to what happens in a regular convolutional layer, but the AGU can handle this. It does it by reordering the sequence of mock operations, and so that it can handle complicated transposed convolutional layers with stride and dilation that are greater than 1. And those of you who are familiar with this type of convolutional layer may imagine how complicated and how sophisticated are the state machines inside this AGU. Finally, I want to show 2 examples of two-dimensional convolutional layers that we implemented on the HAIUT. The
If I
first one,
if I could cut you off for a second, maybe we have maybe
yeah.
1 more minute. So if you could maybe just show one more example and then we can finish if that's okay.
Okay.
Thank you.
So this example is sound event detection. It can detect glass break and standard alarm sounds like T3 and T4 and baby cry. And it consists 2 convolutional layers and 20 convolutional layers and 2 fully connected layers, and consumes only 430 microwatts. And the second example is for face detection. You can see how this neural network can detect the face, and it makes a red rectangular around the face and 5 landmarks over the eyes, nose, and mouth. And it consumes about 1 milliwatt, and it is made of 4 convolutional layers and 4 fully connected layers. Finally, we have a chip that already accommodates this Net light with the SIVA TIC Light 3 side by side, and they can run in parallel, and for algorithms that also have some neural network inside. Okay, I think that's all. Thank you, and see you in the questions and answers.
Thank you very much, Moshe. This was great.
You're welcome.
I'd like to acknowledge our sponsors. First, it's ARM that develops software and hardware for tinyML. Qualcomm, Samsung. These 3 are the executive sponsors. And then followed by platinum sponsors: ETA Compute, Lattice Semiconductors, and the gold sponsors are BrainChip Corporation, Cisco, DSP Group, H-Impulse, EMSA Visual Sense, General Matter Labs, Green Waves Technologies, HIMAX, Imagimob, Latent AI, Maxim Integrated, Kixo, Reality AI, SenseML, Silicon Labs, Sentient, and Google TensorFlow. XMOS, and the silver sponsors are H-Cortex, HOTS, and SynSense. Again, we are very grateful for their continued support, and this is a great testimony that the foundation and this community is really of huge interest for the companies and for the whole world.